Okay, so now we're going to look at the strength of acids and bases. So we've introduced ourselves to areneous acids and bases, which donate protons or donate hydroxide ions in solution. Bronsted-Lowry acids and bases donate or accept protons, right, respectively. And now we're going to talk about strengths of acids and bases. So this is really subtle. It turns out that weak acids only partially dissociate in water. So if I told you that HF was a weak acid, if I told you it was an acid, you might expect that it would dissociate into fluoride ions and hydronium ions, right? Because the H plus would be donated to water molecules. However, it's a weak acid, and what that means is they don't all donate. Only some of them do, okay? And the extent to which they dissociate or donate those H pluses is the extent to which we would call them strong, okay? Strong acids dissociate completely, and weak acids don't, and the weakest acids barely dissociate at all. So hydrofluoric acid is the only halogen that forms a weak acid. We're gonna memorize the other ones here in a little bit. Our learning goal for this section is to write equations for the dissociation of strong and weak acids and identify the direction of the reaction. Okay, so a strong acid ionizes completely. That is, if you put HCl in water, it goes 100%, and that's why we do a single directional arrow right there, right? So that means all of the HCl dissociates into chloride ions, and it donates the proton over to the water molecule, making it hydronium. A weak acid doesn't go 100%. So if I have carbonic acid here, some of them donate the H plus, right? But we show this bidirectionally to indicate that some of them don't. So if you look at a bucket of these things, you're going to find both HCO3 minus in it, which we call bicarbonate or hydrogen carbonate, and we're going to find carbonic acid, both of them in solution. They do not all go, okay? So again, another way to look at that is a strong acid, and we did like a bar graph of a strong acid, HI, hydroiodic acid is a strong acid, and 100% of the HI is dissociated. We don't see any HI left at the end of the reaction. None of it. Okay? However, a weak acid, that is not the case. With hydrofluoric acid, if we go back and forth, it turns out a lot of the HF stays as HF. It doesn't react. Only some of it donates its protons. All right? And that's the difference between a strong acid and a weak acid. So here's a nice table. Table 11.3. There's a lot of information on here, but let's just sort of go through it, okay? Strong acids are HI, HBr, and HCl. Okay, those are three on the periodic table. Iodine, bromine, and chlorine, right? And then more strong acids are perchloric acid, sulfuric acid, and nitric acid, and hydronium. Okay, those are the, I guess, 7 strong acids, right? Now, if we take away the H plus from HI, we see that it is simply iodide, left, right. HBr leaves bromide in its wake. HCl leaves chloride in its wake, right? I think you can figure out the rest of those. Weak acids now include the following. Everything that's not, by the way, everything that's not up here is a weak acid. So this is only a sampling of the weak acids. But hydrogen sulfate, HSO4, hydrogen sulfate dissociates to SO2, SO4 minus, right? Phosphoric acid goes to H2PO4 minus, right? Hydrogen phosphate. These are all weak acids. Nitrous acid is a weak acid. It goes to nitrite, right? Let me point out that nitric acid is up here. Nitrous acid is down here. Okay, these are more examples of weak acids. So, strong and weak acid dissociation, we've already said this, but I want to say it again. In an HCl solution, the strong acid HCl donates 100% to form H plus and Cl minus. The solution of a weak acid, acetic acid, this is acetic acid right here, contains mostly molecules of acetic acid, with only a few that have dissociated. I've said that a couple times now. I'm not going to show that picture again, okay? I do want to talk about diprotic acid. So carbonic acid is a diprotic acid. And what that means is it's got 2 H ions that can donate. When one of them goes, right, when there's missing right here, When one of them goes, it still has one left. We call it hydrogen carbonate or bicarbonate, right? Hydrogen carbonate or bicarbonate. And that is the essence of baking soda, by the way. Sodium bicarbonate is that with a sodium ion associated with it, okay? Now, if the other one gets donated, then it's called carbonate, CO3 2-, okay? Another diprotic acid is sulfuric acid. After it donates the first one, it goes to HSO4-, right? And HSO4- can also donate one, and that becomes SO4 2-, right? Can you see that? Okay, so let's talk now about strong bases. Strong bases are strong electrolytes, and they're formed from metals in groups 1A and 2A. For example, lithium hydroxide, sodium hydroxide, potassium hydroxide, barium, strontium, and calcium hydroxide. They dissociate completely in water, and that's why we call them strong. They dissociate completely in water, and so we use a single directional arrow there, and we call them strong. Weak bases are anything otherwise. Okay, so ammonia is a weak base, and ammonia goes back and forth, right? So if you see a solution of ammonia, which you probably have in your Windex bottle, then you're going to have a sizable population of ammonia and a sizable population of ammonium ion. Okay, strong and weak bases. We've already told you about the strong bases, right? But weak bases are everything it's not, right? Sodium hypochlorite, sodium phosphate, sodium carbonate, right? Sodium carbonate again, right? These are what they're used for, okay? Now, the direction of a particular reaction depends on how strong or weak an acid is. So strong acids have weak conjugate bases that do not readily accept H+, all right? Because they're weak. As the strength of the acid decreases, the strength of its conjugate base increases. As the strength of an acid decreases, the strength of the conjugate base increases. In any acid-base reaction, there are two acids and two bases, depending on which direction you're going, right? One acid is stronger than the other, and therefore we would say that we can determine the direction of a particular reaction. For example, look at sulfuric acid, which is a strong acid, and look at hydronium, which is weaker. And if that's the case, we're going to say that the direction of the reaction is going to go toward the weaker acid, right? Because hydronium is a weaker acid than sulfuric acid. Okay, let's look at another example. If we take a weaker here's a base, right? Just a second here. Yeah, there's a base, and here's a base, right? So we know that the stronger base, let's see, I'm sorry, this is something to look right about this. Yeah, okay, so here's the stronger acid, and here's a weaker acid. That's what we said earlier, and I want to just keep with that language there. The reaction is going to tend toward the weaker acid, right? The stronger acid is going to go to the weaker acid, all right? And we can say the same thing about the base. The stronger base is going to tend toward the weaker base, and so that's going to help us predict the direction of the reaction, okay? So pause the video and identify each of these as a strong acid or a weak acid, or a strong base or a weak base. Okay, I'm going to suppose you paused it, and I'm going to look at these with you. Here is a strong acid because we memorized it as a strong acid. Here is a strong acid because we memorized it as a strong acid. There's a leading hydrogen, so it's going to be an acid, but it's not on our list of strong acids, so it's going to be a weak acid. Weak acid. Weak. Okay? And here is a strong base because we memorized it, right? And this one's not in that group, so it's going to be a weak base, copper hydroxide. Okay, pause the video and tell me which of these is a stronger acid or in each pair. Which of these is a stronger acid? And you're going to want to use this table up here. As a matter of fact, I'm going to copy this table and put it down there. I'm going to C and B. Which of these is the stronger acid in each pair. Pause the video and come back and look at your answers with mine. Okay, so I'm going to do this now. Let's go with blue first. I'm going to look for nitrous acid here, and it's HNO2, right? It's here. And H2S is here, right? And this is increasing acid strength. And so this is going to be the stronger of the acids because nitrous acid is higher. Okay, let's do it in red now. Hydrogen carbonate. Hydrogen carbonate is here, or bicarbonate as it's called here. And HBr is here. Definitely HBr is the stronger of the two acids, right? Okay, so let's do this last one here. Phosphoric acid is here. Phosphoric acid is here, and hydronium is here. And hydronium is the higher of the two, so that is the stronger of those two. All right, so we've talked about acids and bases in terms of their strength and weakness. And that's what this section is about. You'll get a chance to practice this in your homework. Good luck.